So today we are going to discuss a demo session on VLSI chip design. Okay. Have you gone through the session, whatever I have shared before?
Yes, ma'am.
So you will get some idea what is meant by VLSI and what is the history of VLSI and what are the current technologies we are using like fabrication technology or chip technology and what is the future of VLSI. So you will get these things, the basic knowledge from that session. That's why I told you to just go through the session so that the remaining topics, some few advanced topics we can discuss in this session, right? Okay. So I think you all went through the session because as a fresher, as a first session, you'll have some enthusiasm to know the new things, right? So I think you all went through that session. So we'll discuss few points from that session. Okay. So can you tell me what is meant by VLSI design?
Designing of millions of transistor in a single chip.
Okay. Any other answers?
And VLSI means a very large scale integration. Here, the number of transistors is fabricated in a single chip.
Okay. Okay, that's good. So can you tell me what we have discussed in first demo session, like whatever I have sent to you? Can you tell me what is mean by Moore law and how the Moore law is executed nowadays? What Moore predicted?
Moore law said the numbers of transistor will double every 2 years.
Okay. So the number of transistors will be double for every 2 years, approximately 1.8 year. Okay, not 3 years. So that is the Moore law. Whenever the transistor, number of transistors are doubling, okay, at the same time, the size of the transistor will be half approximately for every 2 years. Okay, so that is the Moore law. And now in this today's session, we will discuss some more technologies in the VLSI. Okay, like chip fabrication technologies and what are SOCs, how we can design SOC. If you go with the VLSI as a design engineer or verification engineer or physical design engineer or any DFT engineer, whatever. So, what is the main intention of each field? Okay, so today we'll discuss all these things. Whenever you feel some doubt and all, whenever you didn't understand the topic, you just raise your doubts. We can discuss more briefly. Okay. So, do you have any doubts in first demo session, whatever I have shared? Do you have any doubts in that session?
No, ma'am.
Okay. So if you don't have any doubts, we'll move to the next. So, yeah, is there any doubts? Okay, see here, the key milestones in the semiconductor industry. I think you already know the semiconductor industry, like how the chip fabrication technology has evolved from the different transistor families. Like one of the first computer we have used the vacuum tube technology in the first computer, right? By using the vacuum tube technology, we can do the multiple operation in the sense that time we can do only a simple operation like addition or subtraction, but nowadays we are doing multiple arithmetic and logical operations with several instructions, right? So from vacuum tube technology to diode family, so from the diode family we have moved to the transistor logic. In the transistor logic, different type of transistors are evolved. right? Like BJT transistors or FET type transistors. In FET type, we have used MOSFET or CMOSFET, then FinFET technology. Several type of transistors we have used from past few years, right? I think everyone know the history of the VLSI. So if you see, just we'll discuss a brief on that. So in 1947, the researchers or scientists invented the transistor. Okay, who invented the transistor? Not a single person, different people like John Bardeen or William. So they all together invented a transistor. So the transistor has replaced the vacuum tube technology. Vacuum tube technology means previously 20 years back also you may see the television. In television there will be very big size televisions will be there, right? A very box size, and there will be long tube. That is nothing but vacuum tube technology. Same technology we have used in the computer. But first computer, that is a very big size, a room size computer. From that, we have reduced the size, and we have used the transistor logic family in the to integrated the circuit for the circuit functionality. And then in 1958, can you please mute your systems? Okay, so in 1958, integrated circuit, IC. So what is mean by integrated circuit? If you are second year or first year, maybe you don't know. From third year, you will get some idea what is meant by integrated circuit, right? In your laboratories, you will see, you will find some IC, right? There will be one IC like this, and there will be side pins will be there. Okay, whatever we are using in laboratories, that is very small for simple operations. We use that type of circuit. But in your laptops or mobile phones or any digital circuit, any digital gadget, your like watch, okay, digital watch or any digital gadget or even ATM machine, ATM card, it also have some chip, right? The chip is nothing but some integrated circuit. Okay, so integrated circuit is nothing but the transistors. Here we invented the transistor. In the transistor, we have different type of transistors like a BJT, FET, CMOS, and all. That the combination of transistors is nothing but integrated circuit. Okay, in the integrated circuit, we are putting millions of transistors, multiple transistors, and some type of components we are integrating on a chip. Okay, that's what we are calling as a integrated chip. Okay, from the integrated chip in 1971, the first microprocessor has introduced. Okay, so what is the first microprocessor?
Intel for bit.
Intel 4004 microprocessor has introduced. Okay, from that microprocessor, we can able to integrate some CPU on a single chip. Microprocessor is nothing but central processing unit, right? So from that onwards, we can integrate a CPU on a chip. And if you know the chips, whatever the computers we are using before, those are very complex, bulk in size. Okay, like this much of bulk in size, and if any chip has more heat, we will use some extra fans to cool the chips and all. Maybe you will get some idea, right? So that's what the first microprocessors looks like. Okay, very big size. But currently, we are not using that much of big size. Very smart chips we are using, because day by day the size is reducing whenever number of transistors are increasing. Okay, from that microprocessor in 1980, VLSI chips are introduced. Okay, so what are VLSI chips? Nothing but whatever we are seeing, the integrated circuit, which is having millions of transistors on a single chip. Before VLSI, we have small scale integration, medium scale integration, like that. We'll see the classification also. From the VLSI chip, we are using system on chip. So what is the difference between VLSI and the system on chip SoC? VLSI is nothing but it is a integrated circuit where we can put different types of chips integrated with each other. Okay, suppose there is a CPU. CPU will be integrated to the memory module, and memory module should be integrated with some other graphic processing unit, and then it should integrate with some RAM modules. Like that, we will integrate one to one each other. But whereas system on chip is a very advanced technology in the semiconductor industry. Okay, so here, by using the system on chip, we can integrate the entire system in the sense every block. Okay, whether it is a CPU or memory unit or graphic processor unit or any type of ports, we will integrate on a single chip. Currently, whatever you are looking in your laptops, okay, whatever the laptop, Mac or any laptop and mobile phones, whatever we are seeing, all it contains the system on chip. Okay, from the system on chip in 1990s, nanotechnology also introduced. What is the nanotechnology? From the macrometer technology, we are coming to the nanometer technology. Okay, for more efficient performance, and it will reduce the power consumption because the size is reducing, right? From macrometer to nanometer, the size is reducing. Whenever the size is reducing, what happens? Automatically, the power consumption will reduce and number of transistors also increase in the chip if size is reduced. Okay, so that is the nanometer technology. And FinFET technology. From the CMOS technology, we are we have moved to the FinFET technology. If you go to the old demo session, there you will understand what is the difference between CMOS and the FinFET. Okay, so can you tell me how we can how can we calculate the size of the transistor? How can we calculate the size of the transistor? What is the difference between CMOS transistor and the FinFET transistor?
Uh,
Yes, tell.
Pero compadre, oh.
ma'am,
Hello.
in FinFET, there is a multi-gate transistor, ma'am.
Okay. Any other answers? What is the difference between CMOS transistor and the FinFET transistor? If you have gone through the previous session, you can answer. What are the limitations with the CMOS transistor? Then why we are moving to the FinFET transistor? So, transistor is nothing but here CMOS transistor means it contains source, drain, and gate terminal will be there. And here the distance between source and the drain is nothing but the channel. This is the channel width. So the electrons flow is in this direction, source to drain, right? So whenever we are reducing the size of the transistor according to the Moore law, suppose in 1947 it is the size is in micrometer. Currently in the nanometer technology, we are using nanometer size. That means from 100 micrometer, 10 micrometer, 5 micrometer to 1000 nanometer, 500 nanometer, 100 nanometer, 10 nanometer. Like that, we are reducing the size. Okay. So while reducing the size, okay, we are taking number of technologies, number of transistor technologies, right? Like a CMOS or FinFET, or before we have used JFET, like that. Currently, we are using GAFET. So in every technology, what is happening? There will be some cutting edge will be there. That means, suppose this is the CMOS transistor. Okay, CMOS transistor is starting from 100 nanometer to around 24 nanometer, like that. Once it reaches to 24 nanometer, it have some limitations like a short circuit effects and the current leakage effects will be there. Okay, so why the current leakage effect, short circuit effects? Here the size of the transistor is nothing, but if you are telling in the micrometer, suppose here the distance between source and the drain is 100 micrometer. Okay, but whenever it is coming to the nanometer, the distance between source and the drain will be reduced. Very, very small distance. Nanometer means even we can't see, right? So the distance between source and the drain is reducing. Then what happens here? Because two are conducting materials, source and the drain are conducting materials, right? Using the silicon. So the current leakage will be affected here. Current leakages will be there. Short circuit, maybe both, there will be no channel, right? So both material can be short circuit. So because of short circuit effect, the transistor doesn't work. It's a own functionality. Okay, so from the CMOS, we have moved to the FinFET transistor. What is the FinFET? Same CMOS only, but whatever we have taken the gate here, the gate is not taken in a horizontal fashion. Okay, we will consider as a vertical fashion in the FinFET. If you go through the before demo session, there you will find the diagram of FinFET. Okay, like that, FinFET also have the limitations once it reached to the 10 nanometer or 7 nanometer. Again, the distance between source and the drain is reducing. Again, it will have the short circuit effect. From that, we are using GAFET technology. Okay, gate all around. So by using GAFET technology, we can use up to some extent, like up to 5 nanometer or 4 nanometer. Beyond that, again, it will get some short circuit effect. So from each technology, what we are doing, same transistor only, but the how we can minimize the effects, how we can minimize the limitations, like that we are manufacturing the transistor according to our usage. Okay, by avoiding the limitations like the GAFET, nanosheet, MACFET is nothing but nanosheet. Like that, we are reducing the limitations. Okay, we are overcoming the limitations in each technology. So that's why in 2000, FinFET transistors are introduced, and 2010 3D stacking advanced nodes are introduced like nano nodes. And currently, once the transistor is reduced to 1 nanometer, 1 nanometer means the source and the distance between source and the drain is very less. Okay, overall the transistor will be short circuited. Currently, we are using 5 nanometer, right? 5 nanometer, and some companies are using 3 nanometer processors. Okay, but once it reaches to 1 nanometer, what happens? So here, some quantum technology is introducing here. Okay, so quantum technology is nothing but it is in an atomic level. Atomic level means whenever it is reduces to 1 nanometer, it doesn't have many electrons, right? The huge number of electrons it doesn't contain. Only we can treat just few number of electrons like 1 or 2 or below 5. Okay, in the atomic level, we are going to store the data. Up to now, by using the transistors, we have stored the data. Okay, if transistor is 1 on, it stored 1 bit. If transistor is off, it stored 0 bits, right? So whenever the transistor is not working with its functionality, we are going to the beyond, that is nothing but quantum technology, quantum computing. So by using the electrons and neutrons, protons in the atomic level, we are introducing this technology. Already the researchers has introduced this technology, and currently many of the companies were working with the quantum technology. Okay, in the quantum technology, there are so many things to learn. like how we are going to store the data in a electron, what are the quantum bits. If you are interested, just go through some papers, some IEEE papers and some research papers are available. Otherwise, I will share you. Just go through how the data is going to store in the quantum computing. Okay, what is mean by qubits, how fast the qubits will work compared to the normal bits. Okay, and what is the like principles of electron, what are the superposition principle or entanglement principle. Just go through all this topic, you will get some idea of future technology of VLSI, how the VLSI is going to collaborate with the artificial intelligence, how the machine learning is going to involve in the VLSI in coming 10 to 20 years. Okay, so many journals are available, just go through the. Okay, if you, I can share you after this session. So the artificial intelligence and machine learning importance in VLSA, how they are collaborating in future. So these are the things you need to know, basic things. Okay, everyone understood up to here?
Yes, ma'am.
Do you have
Yes,
any
ma'am.
doubts? Do you have any
No, ma'am.
doubts? Smith, Kiran, Asma, Varun, Vamsi, Satyam, Shanif, Sharath, Trevin. Do you have any doubts?
Ma'am,
Dheeraj? Yeah, tell.
ma'am,
Mm.
if we hear that in a mobile technology there is a 3 nanometer transistors are available. Is it there all the transistor are 3 nanometer or a particular transistor,
Each transistor is a
particular
3
number
nanometer.
of count are in 3
Your voice is not
nanometer?
proper. Your voice is not proper. So whatever the billion number of transistors will be there, right? So each transistor size will be a 3 nanometer. Okay. So this is the Moore law. Okay, Moore law is nothing but the number of transistors in an integrated circuit will be double for every 2 years, and the size of the transistor will be half for every 2 years. Okay, so you can understand the before chips how much the bulk in size, and currently what the chips how much uh, less size, right? Very smart. So that is the difference, and the speed wise also, speed wise and power consumption wise. So before you can't take the any mobile phone, you cannot use for multiple purposes, you cannot run multiple applications in the mobile phone, but currently we are running multiple applications at a time in the mobile phone, right? So multitasking it is performing because of processor only. These all things happening because of processor only. Okay, and its advancement. So this is the classification of integrated circuit. Up to now, we have seen very large scale integrated circuit, right? So how the very large scale integrated circuit has evolved. So from small scale integration, it have only 10 number of gates, that means less than 64 number of components in 1964. And then we have moved to the medium scale integration, nearly 100 number of gates, and then large scale integration, nearly 10,000 number of gates, and very large scale, 1 million number of gates, ultra large scale, 1 million, more than 1 million gates, and grand scale, GSI, grand scale integration. So like that, different type of classifications are there in integrated circuit. Okay, like a grand scale or 3D IC, non-planar IC, like wafer level integration. These are the super chips, whatever we are using in the SoC level. Okay, so these are the different classification of integrated circuits. Do you all got the idea, everyone? Hello,
Yes, ma'am.
is there any doubts, others? Is there any doubts from others?
No, ma'am.
Okay. So next, evolution of processors. Okay. So different type of processors, right? Here I have mentioned a few type of processors. See here, Intel 4004. Okay. With a 108 kilohertz clock speed and PMOS transistors nearly 2300 with a 10 micrometer technology. And in 1976, 8085, you will have the lab also, 8085 microprocessor. How you will write the coding for microprocessor? There will be instructions, right? Using the instructions, you will write the program. So that thing also we'll discuss now. So that is the Intel 8085. And then in 1985, 80386. Total 275 number of transistors, 75,000 number of transistors with 1 micrometer technology. And in 1993, Intel Pentium, okay, so with a million number of 3.2 million number of transistors with a 0.6 micrometer technology. Like that AMD processor or Intel Pentium 2 or AMD Athlon and Intel Pentium 4. So these are the different type of transistors we have seen up to now. In 2042 million number of transistors we have used under 0.18 micrometer technology. And next, in 2003, Intel Pentium M with a 77 million transistors. See, in terms of speed also, from kilohertz to gigahertz. Okay, kilohertz to gigahertz in terms of speed, and 0.13 macrometer. From Intel Core 2, from here, number of cores are introduced. Number of cores means number of multiple tasking will be there. Okay, number of instructions will be executed with number of cores. Okay, so speed will be high. So 1.86 gigahertz, 291 million number of transistor in nanometer technology. From macrometer to nanometer technology we have moved. Okay, and then 2008 Intel Core Quad. In cores only will partition it into in terms of quad. That means 4. Okay, so in core only there will be CCX1, CCX2, CCX3, CCX4, like that. In terms of cores we will have, and 820 million transistors and 45 nanometer processor from 65 to 45. Okay, for every 2 years it is size is reducing. Okay, and in 2010 ARM Cortex. Okay, see the clock frequency and 32 nanometer and 22 nanometer process. Like that, 2011, 2012, billion of transistors we are using under 22 nanometer. Okay, so these are the different type of processors. All these processors we have seen already in our laptops, mostly in the laptops and the mobile phones. So these are in 2012 AMD processor, and 2013 with the FinFET technology. Up to here, we have used the GAFET technology up to 2012. From 2013, now we have used the FinFET technology for 16 nanometer. Okay, currently we are not using 16 nano FinFET technology because FinFET technology is up to 7, below 10 to 7 only. Okay, so this is the Intel 4004 Pentium processor. See how much difference is there. Number of blocks also more, right? And here coming to ARM Cortex, individual processors are there. Okay, one CPU, two CPU with n number of cores, non-CPU circuit. That means some other logic circuit, some other IPs related to the different. Okay, so this is the difference we are seeing. But currently, what type of circuits we are using? Like SOCs, okay, like quad core, octa core, these type of cores we are using. Okay, do you have any doubts up to here?
Ma'am, what is thread?
Sorry?
Thread means ma'am जो which are in laptops like 2 core and efficient core, and that is comes after thread.
Thread in the sense a number of instructions it will execute. Okay, 8 cores, 16 threads like that it will have, right? So 8 core CPU with the 2 threads. Each core it have the 2 threads for executing any task. Okay, if there are more number of threads, the execution will be fast. 8 core, 16 thread, 8 core, 8 thread, like that. That means each core it have the task execution. So based on that, it will boost. Boost the speed. Okay. So multi-threading means if you have the multiple threads, it will run the multiple process. Okay, all instructions it will run multiple multi-threading. So that is what concurrent task can be performed simultaneously.
Okay, ma'am.
Okay, do you have any doubts up to here?
No.
Okay,
No,
so
ma'am.
this is the VLSI design flow. I think everyone got the clarity on what is meant by VLSI integrated circuit and how integrated circuit has introduced like evolution. So all these things everyone clear, right? So another main important thing is VLSI design flow. So we are talking
This is
about
I
different. Can you mute? Okay, so up to now we have seen different VLSI circuits, right? Small scale or medium scale, whatever, like ASIC chips or FPGA chips. Okay, so to manufacture a chip, a integrated circuit, we need to follow all these steps. Several engineers will be involved. Lakhs of engineers are involved to design a integrated circuit. Okay, so first we'll see the design flow. I think already you know the design flow from the first demonstration, right? But again we will discuss. Okay. So first thing is the system specification. In the VLSI design flow, first step is the system specification. Any engineer, any VLSI engineer, if they want to start some work, okay, with their team, first, he or she need to know the specification of their project. There are several projects will be there in SOC level or in IP level or normal projects. Several projects will be there. Every project has its own specification, right? Suppose if you want to design a traffic light controller, okay? So traffic light controller have its own specification. How many number of lights should have, like red, green, yellow, and for each light, suppose current red is there, so it should have some delay, right? Then next yellow or next green, every light should have some delay, and every light should on for some certain time. So according to that specification, you will understand what you need to design, right? So once you got the idea on the specification, okay, you will design manually. First of all, what are the inputs, like clock reset or control signals will be there. According to that, you will draw some block diagram based on the inputs and the outputs. Once you draw the block diagram, you need to write the logic design. Okay, can you all please join for the next session quickly, because this session is limit for 40 minutes. Okay, by using the same link you can join again. Can you join
Okay, ma'am.
again by using the same link? Yeah.
Okay.
Yes, ma'am.
Okay. So first you need to understand the specification. Okay. So in the specification, everything will be mentioned clearly. So you need to understand the specification first, then functional design and the logic design. Okay. You need to write the functional design. How you will write the design? Mainly we will use either Verilog HDL or VHDL to write the program. Okay. So here there will here we will have the specification. According to that, we'll draw the block diagram and we will write the program using the hardware description language. Okay, we have the hardware description language like Verilog HDL or VHDL. Based on that, you can write the design. Okay, you will generate the circuit netlist. We'll discuss that also, how to design the circuit netlist. And then once circuit design is completed, next important thing is verification. Okay, after this circuit design, verification will be there. Verification in the sense, by using the higher level languages like a system Verilog and UVM methodology, by using the methodologies, we can do the verification. Why we are using UVM methodology and system Verilog? Because we are using SOC level circuits, right? SOC type circuits or very complex circuits we are using. Okay, very complex circuits in the sense it have some higher functionality. Okay, for that purpose we are using the UVM methodology, which can support the randomization. We can randomize a very any type of scenarios. Okay, according to the specification needed, we can generate any type of scenarios or coverage analysis. There are some high level features will be there which support some high level features. That's why we use methodology for the verification. Okay, in the coming days, if you are interested for the training, you will understand those things. And then back end. So front end is the design and the verification. This is the front end, design and the verification. Back end is the physical design. What is the physical design? First, in the physical design, there will be partitioning. Partitioning in the sense, we'll take the silicon chip wafers. There we will do the circuit with different IPs in overall SOC, partitioning and chip planning, how we can integrate the digital circuit in the chip plan and the placement. The whatever we are generating here, synthesizer circuit netlist, then that we need to place in the silicon wafer hardware. Clock tree synthesis, signal routing, timing closure. These are internal sub blocks, sub we need to work on this. Okay, clock tree synthesis means that is a separate domain. Okay, domain in the sense like separate group. Okay, separate team. So clock tree synthesis. So every digital circuit have its own clock, right? If you go for SOC level, those are very complex things. Okay, so there we need to check all different clock signals and signal routing. Okay, all signals are matching with the inputs and outputs or different IPs or not, and timing closure. We need to check all these things with the different teams are available. And physical design verification and sign off once chip fabrication completed. Okay, sign off in the sense once all will have the timings. Okay, for every month we'll have the the meeting will be there, right? So once step of completed, like we'll go to the fabrication technology. And then packaging and testing. So packaging and the testing means once all these things are completed, we will integrate, we will make some into the silicon wafer, we'll put into the packaging. Okay, and then chip in the sense the ready-made integrated circuit. Okay, so these are the various steps we need to follow to manufacture a VLSI chip. Okay, so in VLSI chips, we have different type of VLSI chips. One is a ASIC and FPGA. We will see the difference. Have you understood up to here VLSI design flow?
Yes, ma'am.
Others? Why others are not responding? Have you not understood? Just ask your doubts. Whatever you have the doubts, you can ask.
Ma'am, it is necessary to write the test bench in system Verilog and UVM.
Sorry?
Is it necessary to write
Yes.
the test bench
Yes.
in system Verilog?
Only system Verilog and UVM are considered to write the test bench in industry, every company. Either system Verilog, UBM, or C language. C language is the sense will not write all blocks, only for processor verification we'll use the C or C++. I will tell that thing why. Okay, have you understood up to here? Okay. Next is, what is the difference between ASIC chip and FPGA? Can you tell me what are the differences?
Ma'am, ASIC is a application specific integrated circuit. It is manufactured for a specific application. But in FPGA, it is for general purpose. We can reprogram it for as our requirement. But in ASIC, it is not programmable after it it is manufactured.
Okay. Any other answers from others? Okay, so ASIC chips and the FPGA chip. So whatever we have seen here, okay, to do any, to manufacture any integrated circuit, we need to follow all these steps, right? So that integrated circuit is nothing but a permanent chip. Those type of permanent chips we can call as a ASIC chips, application specific integrated circuit. Okay, nothing but the processors, whatever we are using, the microprocessors and all. Those are used for only specific use. Once the manufacture is completed, we cannot do the reprogramming, because why we can't do the reprogram? Because according to your particular specification, okay, we will manufacture according to that usage. We cannot use that multiple purpose by reprogram it again and again. Okay, so at the manufacturing time only, whatever the circuit diagram you are generating here, you are generating the circuit diagram according to your specification. That same circuit diagram you are dumping into the silicon wafer, right? Again, once the silicon wafer hardware is manufactured, that is a permanent one. We cannot do the reprogramming of the chip. Okay, that's why ASIC chips are permanent chips, like your processors, whatever the chips you are using in the digital gadgets, those are the ASIC chips. And FPGAs are the reprogrammable. FPGA is nothing but field programmable gate array. It will be look like this. Okay, I think as you are graduates, you know Arduino in the IoT, right? Most of the students nowadays, they are working on IoT projects. There will be Arduino, or if you work on embedded system projects, there will be Raspberry Pi. That means why we use those? Whatever the specific functionality you want to work, like whatever the project you want to implement, by using those Arduino or like a Raspberry Pi chips, so we do the programming. We dump the programming into those kit and we can develop some project, right? FPGA also same. Okay, but here this is a hardware description. Okay, so FPGA or used in VLSI. So same, whatever the project you want to implement, you can dump the program into the FPGA and you can use the for particular project. Again, if you want to reprogram it for some other project, you can again reprogram it. That is the difference between ASIC and FPGA. Okay, most of the companies, whatever they are they are manufacturing the chip. Okay, they are introducing some processor. They won't directly do the manufacturing with the ASIC chip. First, they will confirm with the FPGA chip only, because FPGA are reprogrammable, right? If any mistake is there, if any error or debugging things are there, we can easily do that. But if you do directly with ASIC chip, the cost, if any circuit mismatch or any connections are wrong, the whole chip will be spoiled, right? That's why they will check with the FPGA. That is the difference between FPGA and the ASIC. Okay, if you go for any interviews and all, these are the basic interview questions you need to know before entering into the VLSI domain. Okay, that's why we are covering these things today. And next thing is the system on chip. So we have seen up to now the ASICs and the FPGA, right? So like that, there will be a system on chip. System on chip in the sense, if you see here, the processor different type of this is one IP. Okay, this one box we will call it, sorry, this small box we will call as a IPs. Okay, IP in the sense intellectual property. Like here in this, it will have some digital circuit. Okay, some core related circuit. Here cache memory is there. Some cache related circuit will be there. And here some DSP, digital signal processing circuit will be there. So this number of IPs is combinedly called as a subsystem. Okay, and these big blocks are called as a subsystem. All these big blocks are called as a SOC. Okay, these all will call overall circuit is called as a SOC. These type of SOC you will see in your mobile phones or in your laptops. Okay, this is what actual SOC there in the uh, will be there in the mobile phones or the laptop. Okay, this is a basic, but every industry, every company, but what are the companies generate the SOC like Intel or AMD or ARM, okay, Samsung. These companies have their own SOC architecture, but this is the basic SOC architecture. Okay, if you move forward, I will show you the exact SOC architectures of different companies and how the SOCs are built. All these things we can discuss. Okay. And so in each SOC, there will be some CPU related central processing unit. Here we have used ARM Cortex CPU subsystem. So there will be some memory subsystem. In memory, it will consist of different memory controllers. These are high level things. Once you are working with the projects in system Verilog, there you will understand what is meant by USB, PCIe, UART, I2C, AMBA protocols. So how these interconnects, these interconnects, how we can program. Okay, all these things are related to the VLSI. Okay, so we won't generate all the things by single team or like that. There are several teams, thousands of teams involved in the like any project. Okay, so if you want to develop a single IP, there will be thousands of engineers involved to develop a single IP. Okay, so this is the system on chip. Everyone understood?
Yes, ma'am.
Okay. So here you will find the how evaluation of system on chips in 1995, what type of SOC we have used, 96, 2011, 2013, and in smartphones, what type of SOCs we are using, Snapdragon. Everyone maybe you had, right? Snapdragon from Qualcomm and Tegra from NVIDIA. Most of the processors or graphic processors can be designed by NVIDIA. Like that from Intel company and Samsung company and from MediaTek, Broadcom, Apple. Okay. So these are the different company SOCs you can see. Okay. So yeah. After that, if you see, just now we have discussed the system on chip, right? Here, system on chip. Several blocks are involved in a system on chip. In that system on chip, there will be one block. Suppose if you take a single IP, okay, in single IP, if you take in the single IP, several blocks are involved. 1, 2, 3, 4, 5, like that, several blocks are involved. If you consider this one block as a router, okay, if you consider that one block as a router, so how it will look like? So this is the router. What is meant by router? The router is also a digital circuit which can be route the data between different physical addresses, different computers. Okay, so the router consists of one finite state machine. Okay, before that we will discuss um, what is the importance of digital electronics in VLSI. Can you tell me? What is the importance of digital electronics in VLSI?
Ma'am, maybe it is works on 5 volt or 0 or 1. 0 for off state and 1 for on state.
Okay.
For this, we use digital circuit.
Okay. So, what is the importance of digital electronics means? In VLSI, we have both analog electronics and the digital electronics. Okay, analog electronics in the sense old and is whatever we have used, some of the gadgets and all, those are the analog related. Okay, nowadays also using not whatever you are seeing in the computers, lab, mobile phones, there we are not using, but for some medical equipment and in the military equipment, there we are using some analog circuits and all, okay, in communication wise, but mostly we have came to the digital world, right? So mostly we use the digital electronics only. So if you see any circuit, if you see a IP level circuit or SOC level circuit, any circuit without a digital circuit, it doesn't have, right? Any SOC without digital circuit, it doesn't have any block. Okay. So like that, I will show you a simple router project. Okay, this is a router project. So what are there here? One finite state mission is there. You know what is meant by finite state mission? Complex sequential logic circuit is nothing but finite state mission, right? Next, register is there. So what are the different type of registers? So here, whatever we are using the register, that is different. Okay. While you are learning the program, there we will write, there we will find different type of registers, how to write in a logical way. That is very important. Okay. If you take a multiplexer you can write in a several ways, like a behavioral modeling or data flow modeling or gate level modeling or switch level modeling. Like that, you can write in multiple ways. But writing the code in 20 lines and writing the code in 2 to 3 lines, there is a difference, right? So you need to follow the tricks how to write the program in 2 to 3 lines. Okay. So whenever you are writing the program in that way, so whenever you are integrating several circuits in a one project, there you can minimize your coding and you can develop a project. Okay. And next one is a FIFO. FIFO is a memory related, first in, first out memory. Like we have the RAM memory, ROM memory, right? Like that, FIFO is the one type of memory. So this is a separate digital block. You need to learn how to design a FIFO. Then after writing all these things, you need to integrate with each other. So how can you integrate with each other? That's what you are going to learn from the Wedlock HDL. From starting onwards, whatever the digital electronic circuits are there, from combinational, from sequential, finite state missions, memory, everything. So how you can design using the Verilog? How can you write a test bench? How can you verify a design? How can you synthesize a design? So everything you are going to learn using the Verilog, because Verilog is a hardware description language. It is not like a assembly level language, or it is not like a C language or higher level language, because by using the C language you cannot develop any digital circuit because it is used for only software purpose. Okay, in the digital electronics there will be registers. Registers in the sense store some data, right? So how you will generate this register? This Verilog HDL is designed, meant for designing a register. Like the clock will be there. How you will generate the clock using the C language? It is not possible. That's why separate language is there, Verilog language. Okay, for any combinational, any gate, XOR gate or OR gate, AND gate, NOT gate, how can you generate all these gates? By using the hardware description language called Verilog. VHDL also there, but VHDL is a complex language. Okay, for writing the program or for execution, we need to include standard libraries and all. That's why it is a complex language. That's why we use a simple language called Verilog HDL. Okay, so I will show you a simple example you can understand. Don't worry about the program. This is a project. This is a big project, router project. So after 1 or 2 months training, you can develop these type of projects. You need to develop in this way. Okay. Just now I have shown you the router project, right? What are the different blocks are involved? Like finite state mission is involved, register is involved, synchronizer is involved, FIFOs, like that. So individual blocks we need to write using the Verilog program. Okay, if you see, this is the router. A router finite state FIFO, first in first out. So this is what the program we can write for first in first out. We can write in very simple way, but we need to we need to meet all the specifications, right? That's why I have written in a simple way. This is the specific. This is the code for FIFO. Okay, so after FIFO, there is a finite state mission. This is how we can write the finite state mission um, uh, for a circuit. Like that, register is there. So this is how we can write the register, synchronizer, and top level. In top level, you can connect all the FIFOs here. There will be 3 number of FIFOs here, and there will be finite state mission, and there will be synchronizer, and there will be register. By using all input and output signals, we can connect like this. Okay, this is how we can develop a Verilog program for any type of projects. Okay, so after writing the Verilog program, you can do the synthesis. Okay, after doing synthesis, you will get the same circuit diagram like this. Okay, so that is the importance of Verilog HDL. Okay, is it sufficient to generate only design? Test bench also needed, right, to verify this design. What is meant by test bench? Applying the input stimulus to the design to verify the output. So we will apply the input stimulus different scenarios and we will check the output. Okay, if output is correct according to your theoretical calculations, then okay. If output is not correct, something mistake is in test bench or in design, again we need to recheck. Okay, so that is the importance of Verilog HDL. We can generate any type of design. Okay, in the same way, system Verilog is used to verify the design. Okay, router in the sense that is a very complex circuit, right? So for that complex circuit, we cannot generate a test bench using the Verilog HDL because Verilog HDL have very less features. Okay, we cannot do proper verification. For proper verification, for high level verification, okay, we use the system Verilog and then we use the verification UVM methodology. Okay, system Verilog is a language, but UVM is a methodology. The difference is if you use the system Verilog to verify any circuit, it will take some 4 months or 5 months. Like I'm telling in industry wise. But if you take in UVM, you can implement or you can verify in only 2 months because it have all standard libraries like that. Okay, so many things are there internally. So that is the difference between Verilog, system Verilog, and UVM. So these type of SOC level circuits we will verify using SV and UVM. Okay. Do you understood,
Okay.
everyone? Is there any
Yes,
doubts?
ma'am. In EDA playground, how we generate circuit diagram?
In EDA playground, we can't generate the circuit diagram. We will provide the synthesis and simulation tools separately. Here we can't generate the circuit diagram. We can generate only simulation verification. Analog design in
Okay.
the sense, if you are using analog circuits using the registers, capacitors, those type of analog transistors is there. Those are analog circuits, right? So Verilog will be there for analog design also. You can write Verilog in digital and also analog, but both are different. The syntax and all, both are different. Okay.
Okay, ma'am. Okay.
So is there any other doubts? So another thing is, we have discussed some 8086 microprocessor like that, right? Here microprocessors will be there in a core in CPU, and here remaining all are hardware like normal digital circuit. Okay, all this digital circuit we will write the program using Verilog HDL, using Verilog HDL. But what is the microprocessor language? Microprocessor language is nothing but instructions: add, sub, multiplication, division, like add R1, comma R2, add some accumulator registers or some general purpose registers, special purpose registers, all these things there, right? By using all those instruction sets, we will develop a core, we will develop a processor. Okay, so further processor, we can't do the verification using system verilog or UVM. Okay, for that purpose, we use the C language because it is not a hardware language, right? It is a assembly level language. That's why for verification also we use the C language. Okay, and remaining all these we use the UVM and SP. And for all this, these are all writing in a hardware language, right? So that's why we use the UVM and SP for verification. Okay, design and verification are separate. You need to understand that thing. Everyone clear? Did you got the idea of VLSI? So what are the different fields, different domains, front-end design and back-end design? Have you got
Yes,
the
ma'am.
idea, everyone?
Yes, ma'am.
Okay. Okay, then. If you have any doubts, you can ping in the group. Okay. And also, we are starting a new batch for full-time job-oriented program, the design and verification program. So, if you are interested, you can join for that. Okay. So,
Ma'am,
from
there,
February
ma'am,
first week, we are starting that batch. Okay. We are starting a batch for uh, new people. Yeah, tell.
ma'am, there is a gap, approx 5 to 6 years from graduation. Should I start or can I
Just
start?
ping me. Just ping me. I will tell you. Okay.
Okay,
You
ma'am.
can ping me on
Ma'am,
WhatsApp. I will tell you.
ma'am, it is necessary to learn Python for the VLSI.
No, Python is not required. Python you can learn for scripting, but instead of Python, we can learn Perl scripting.
Okay.
Coding is necessary, but don't worry about the coding because everything you are learning from scratch, right? From data types, what is the data type, what is the operator, what is the Verilog syntax, everything you are learning from scratch. So don't worry, we will train you according to that only. We will give you the lot of assignments. By doing the assignments, definitely you will get the coding knowledge. No need to worry on that. We will start from scratch. So from scratch, if you start, you can develop a good projects.
Ma'am, can you tell about price of course?
Whoever interested, just ping me. Okay, I will let you know the price and all.
Okay, ma'am.
Yeah. So do you have any other doubts? So this is a 6 months training. Okay, first 3 weeks we are concentrating on the digital electronics assignments, interview questions, mock tests, and all. Once digital electronics completed, we will start the Verilog HDL. Verilog HDL is for 1.5 month. Okay, after Verilog HDL, you will learn the projects, 2 projects in the Verilog HDL. Okay. After Verilog projects, again we'll move to the system Verilog. That means up to Verilog, design will be completed. After design, there will be verification. Okay. In the verification, you will learn the system Verilog for 1.5 month, both the theory and the lab sessions, everything will be there. And after that, there will be 2 projects again. 2 projects in the sense, one protocol, one project. Protocols are very important for VLSI. Okay, because see why protocol is important means here DSP to IP is connecting, IP to IP is connecting. Here there is a interconnect. Here there is a big interconnect with different IPs. So how these IPs are connecting here? These are nothing but bus. Bus in the sense parallelly we can send number of data, 128-bit data or 64-bit data. Like that parallelly we are sending the data. These are nothing but protocol, AXI protocol we use. Okay, like that internally one block to another block connections. We use different protocols here. So all these type of protocols we are going to learn in this batch, I mean in this program. Okay, like that UVM also 1.5 month. There also you will learn 2 protocols, 1 project.
Ma'am, is there any placement assistant?
Yeah, placement assistance will be there. Mixed signal engineer is like a digital signal, like um internally there will be so many blocks will be there. Okay, digital signal processors also there. Okay, so by for that digital signal processor connections and all, you need to connect with various block. Analog circuit will be there. Okay, internally. So like mixed signal processor in the sense, whenever we are connecting with the different analog blocks, there we use that mixed signal, digital signal processing, those things. We use Verilog for analog, but analog Verilog HDL is different. Digital Verilog HDL is different because analog have registers, capacitors, some analog transistors. Those type will be there, right? In digital electronics, we have the logic gates, counters, final state machines. So coding style is different for both.
Ma'am, can we skip Verilog and then learn system Verilog?
Yes, first you need to learn Verilog HDL with a deep understanding of digital electronics because digital electronics is very important as a fresher or experience. And then once you are clear with Verilog, then need to learn system Verilog, then UPM.
We cannot learn direct system Verilog.
No. So if you are not good in the digital electronics, no need to worry. We are going to discuss digital electronics also, but digital electronics we won't discuss very each topic wise. Okay, mostly we will concentrate on interview point of view for the digital electronic because in the BTech level you already learned the digital electronics, right? We will give the 3 to 4 weeks time for digital electronics. We will provide the assignments and we will have the interview questions, assignments. Weekly live sessions will be there for digital electronics. From Verilog onwards, we'll have the regular live sessions. Training will be 5 to 6 months. Full training, full
Ma'am,
job oriented.
ma'am, I have learned digital electronics and Verilog
Okay,
from YouTube. Then
okay.
can I join only for system Verilog and UVM?
Yeah, you can join. Verification batch also starting from February 3rd. You can join for that batch.
Okay, ma'am.
Yeah. So do you have any doubts, others? So if you have any doubts, please ping me on group. Yes, don't think like after graduation we will see what we do now with this program and all. We'll see after the graduation, after final year. Don't think in that way. Nothing will be there to do after graduation. Okay, do something before that. Not only this course, whatever you are interested. If you are interested in software, do something before that. Okay. So because by end of your graduation, you will be settled in a good job. Nowadays, if you see how outside, without job, there are jobless people, or so many people are there because they are neglected their BTech or MTech, okay, in their graduation. So they thought like they just neglected the graduation and all, okay. So now they are very jobless. Okay, so whatever you want to learn, just keep concentrate on and do on work on projects. Okay, if you want to go for software side, there are so many technologies are there in software side, either AI side or MI side or ethical hacking side. There are so many data science or so many things are there like VLSI. Everything just work on projects, new things. Definitely you will get the job by end of the final year. But don't think after final year we can see. Okay, that is a very big wrong. Fees
Ma'am,
and all.
wow.
Fees is fees. If you are interested, just ping me. Okay.
Okay, ma'am. Ma'am, what do I get on if I join for test bench like System Verilog and UVM?
System Verilog UVM means System Verilog you will get two protocols, one project. From UVM you will get two protocols, one project. Total 4 protocols, 2 projects you will get with the overall concepts System Verilog and UVM. I will share the demo sessions for System Verilog. Just go through the demo sessions. Okay, you will understand. You will get some idea. Okay.
And can I also got their placement assistant?
Yeah, you will get.
Okay.
ASIC design course. See, you need to understand one thing. ASIC design course or FPGA design course or SOC. SOC is somewhat different, but ASIC or FPGA both are same. In that year, both you will learn Verilog, System Verilog, UVM. But ASIC means we will work on normal like these projects. FPGA means we will work on FPGA kits. Okay, some home automation projects like that. That is only different. Yesterday I got the query like actually he came for FPGA course, but I have sent unfortunately I have sent ASIC design course. He is telling I think you don't know first. You know what is the difference between ASIC and FPGA? He is telling for me. Okay, let it be go.
Okay.
Both are same. Okay, but projects are different somewhat. Okay, is there any doubts still?
From my side, no, ma'am.
Okay, others? Whoever interested, just ping me on group. Okay, ping me personally. I will send the message in the group. Okay, so whatever the doubts you have, just we will discuss later. Okay, because session timing is completed. So whatever the doubts you have, just ping me on group. Okay.